And this presentation is essentially a long answer to the question, why isn't it ready yet? What are you guys actually doing? So it's going to be quite detailed and quite focused on implementation details, because at this stage it is the implementation details that are between us and being production ready. So I'm going to introduce what a distributed file system is and why they're hard and why they are harder than some of the other types of scale-out storage that we do, and then give a really detailed look at CephFS itself, the architecture, and then what we have been doing over the last weeks and months to get closer to being production ready. So file systems fit in as one of the three ways you can access your storage. And when we talk about a distributed file system, a lot of vendors would call that a scale-out NAS. That's the jargon for it. And when we talk about block storage, RBD, some people would call it a SAN. And when we say object storage, some people say S3-like. So the file system is essentially the NAS part of that three. And that's where it fits in with the other Ceph products. So the file system isn't something we're selling as a product at the moment, which means my life is very good and simple at the moment because I have a pure upstream software development role. But at some point, obviously, we would like to get it to the stage where we can have it running in production in your environments and provide support for that. So object storage is increasingly popular, and the reason for that is not necessarily that people want object storage, but the fact that it's easier to implement. It scales out very, very well. You can have a simple consistency model for interaction between multiple clients where the last writer wins for any given object. You only have to think about one object at a time, because most object stores don't provide multi-object transactions. The clients are comparatively simple. You don't have to worry about an object being open or closed or locked, because there's no such thing if you define your object store model that way. Objects don't have links in general, and some object stores can do this, but in general, an object has a unique ID. That's the only unique ID it has. And the only real challenge is how do you map those objects to nodes? And the answer to that in Ceph is the crush algorithm, which is fantastic and powerful, but it only solves the first part of the problem, which is the object store problem of this comparatively simple need to store isolated objects. POSIX file systems are much harder. So POSIX file system is a piece of jargon which essentially means a file system which behaves like a real local Unix file system. Sometimes people talk about network file systems that are not POSIX compliant because they provide a different set of semantics and a different set of consistency rules to what a POSIX file system would. But we like to think we hold ourselves to a slightly higher standard. So it's not just consistent across opens and closes like NFS. It's just as consistent as a local file system would be. In order to provide that, we have to deal with accesses from multiple clients to the same files and provide certain rules, such as if somebody writes a range of data here and another client writes another range here, and they overlap, in that overlapping region, I cannot, on a sort of byte level or page level, just let either guy win. I have to make sure that either one guy gets that whole region or the other guy gets the whole region. Otherwise, I've broken POSIX, and when you try and run a POSIX application on this network file system, it will break. The dependency between inodes in a file system is a killer for scalability, because it means that when I make a decision about where to put one file and where to put another file, I'm not just thinking about, okay, this guy's here, that guy's there. I'm thinking about when I need to do an operation that spans them, how's that going to work? If I'm operating on a file, creating a file, I need to also be looking at the directory that that's in, and the directory that that's in, and the directory that that's in. So that's challenging. The statefulness of clients adds complexity to the system. And there's also a kind of fuzzier issue with implementing file systems, that users have expectations that stem from the original file systems being local. So applications written for local file systems tend to expect the operating system to do quite a lot of caching and latency hiding for them, whereas applications written for object stores sort of understand the limitations of what they're dealing with. And resilience is more challenging in a file system because if something gets lost, it doesn't just affect one thing that you can notice it's lost and lose it. If something happens that affects something high up the hierarchy, that potentially ripples down to everything beneath it. And that means that we have to write things like FSCK programs in order to recover systems if, heaven forbid, data loss does occur. All of this is harder still because of failure cases. So building a distributed file system that works as long as everything's up is comparatively easy. As long as no data ever goes away is comparatively easy. If you had some magic mechanism that would tell you whether a node was alive or not, that would make life easier, but in reality we don't. We have to make sort of subjective decisions about whether a node is present or absent. And that's a general problem in building distributed systems, but it's particularly painful when you have something as tightly coupled as a POSIX file system. Before I go any further, I just want to get some terminology down. So hands up if you know what an inode is. Good, that's what I was hoping for. So inodes are basically files, but they're referenced by a unique ID. They don't have a name at that point. A directory entry is a name for an inode in a particular directory. An inode can have multiple entries, and if it does, it's considered to be hard linked. And a directory is just a special case of an inode. And these things they sort of make perfect sense if you're talking about how a local file system is implemented. And we map them to network file systems as well, but we tend to handle them in slightly different ways. And so you'll see that within Ceph, the distinction between an inode and a entry is there's less of a separation there than there would be in a typical local file system. So CephFS aims to provide a scale-out metadata system. So we address this challenge of how do we take a tightly coupled hierarchical data model and scale it out across a lot of nodes. In order to achieve that, we sort of defer the whole problem of actually storing data to the underlying object store, to the underlying RADOS layer. So both the data in your files and the metadata about your files get stored in RADOS. CephFS does not deal directly with disks at all. And we also do a little bit extra on top of POSIX. So we have an extension for recursive statistics, which means the file system will track the amount of data, for example, in a given folder. You don't have to have a DF process go and recurse down the tree. You can just ask the file system directly how much is in a folder. We also have subtree snapshots. So if you want to snapshot CephFS, you don't have to do the whole file system. You can do individual directories within that file system. And that's not something that all file systems provide, and many file systems which do provide a snapshot feature, it's either at a whole volume level or more of a static subvolume rather than arbitrary subtrees. So CephFS is made up of a client, a server, and some storage. The storage, as I mentioned, is just RADOS. The server is what we call the MDS daemon, the metadata server. And we have multiple clients. We have a user space client which uses Fuse. We have libCephFS, which allows you to build the file system access directly into your application or library. So for example, that's used in a Hadoop binding for the file system. And we have a driver that's inside the Linux kernel as well. So we are upstream in Linux. If you have a recent Linux kernel, you have the Ceph client already on your system. And that's how those fit together. So the important thing about this diagram is that in addition to all of my other OSDs and monitors within my cluster, I have these new servers, the little tree guys here, the metadata servers. And the client at the top, the kernel client, for example, is sending its metadata and its data separately. So the data doesn't flow via the metadata servers. It goes straight to RADOS and takes advantage of all the existing scalability there, whereas the metadata has this special separate path. And that's the path that you end up with, all the way from the application at the top to the disk at the bottom. We go through one of our clients, we go through a network protocol which hits the MDS and RADOS and ultimately ends up on disk. So there's quite a high degree of abstraction from the underlying disks from the point of view of the application. So how do we scale out file system metadata? The answer in a lot of network file systems is we don't. Quite a lot of scale-out filers will scale out the storage of the data, but not the metadata. And for some use cases, that works quite well. If what you're storing on your file system is just disk images, you have a small number of files where the metadata doesn't change much, you just have really big blobs of data, then you might find that that's not a scaling problem. You can get up to sort of whole rack systems with just one single metadata server, which is fine until it's not fine, and you have a more general purpose workload, or you have a higher requirement for scale. So the next most simple option is to have what I refer to as static subvolumes, which is essentially where you have multiple file systems, but you graft them together. So it's a little bit like if you had two XFS file systems and you mounted them as A and B in the same folder, and then you exported that top-level folder as an NFS mount. Well, it looks like one file system, but in reality, you've statically divided it up like that. So to avoid that static requirement, you can have a much more fine-grained distribution if you hash the paths in files and use that as a unique ID to place files. And that's what some systems do as well. That gives you very nice, smooth placement of metadata, but it has a big downside, which is that all the files in a directory have a different hash and end up potentially on different servers. So if I want to list a directory with 100 files in and I've got 100 servers, I'm going to have to talk to all 100 servers in order to list my directory, which should be a very simple, quick operation, but becomes much more arduous and has much more overhead if you take that hashing approach. So in Ceph, we have what is essentially a best of both worlds approach, where we divide the data up by subtree, so directories and their subdirectories and their inodes stay together and we have that locality, but it's not static. They can move around between metadata servers, and they do so according to the frequency of access or the heat of the metadata as it's accessed. So that's a visual representation of that, where that tree is my file system hierarchy, and the colored regions have been mapped off to different metadata servers. Locality is the key thing here. We go a step further than just having the subtree placement for the metadata. We actually store on disk all of the inodes for a given directory in a single object up to some limit. So if you are doing a list on a directory, that's really fast. I mean, it might sound silly to have such a focus on listing directories, but people do a lot of it and they notice if it isn't fast. The ability to move metadata around between servers isn't just useful for partitioning the data, it's also useful for replication of the data in memory. So if you have a read-heavy workload, you have a lot of clients trying to access the same metadata, what we can do is make sure that multiple metadata servers have a copy of that and avoid there being hotspot issues when a lot of clients want to hit one directory. And there's sort of a caveat to this, which is that in practice, we don't just work at the directory level, we work at the directory fragment level, and there is another hashing mechanism down there that kicks in when you reach a certain number of inodes in a directory, but we don't need to go into that. So the actual data within the files, the stuff that's written directly from the clients to Rados, is written in a striped way. So if I have a gigabyte file, by default that's split up into 4 megabyte objects, and they can be found within Rados, identified just by the inode number of the file and an offset into that striped extent. So the benefits for that are fairly clear. We get the full cluster bandwidth, we get our data nicely spread out across the system. That striping is configurable. You can tell us what stripe size you want, and you can also assign multiple data pools to a file system. So in Rados, the concept of a pool allows you to identify a subset of your storage. So for example, you could say, I've got some SSDs, I'm going to set a layout for this directory to be on those SSDs, I'm going to set a layout for another directory to use all my spinning disks. And also, depending on the underlying storage, maybe a different stripe size makes sense there as well. Another little implementation caveat to this, all of the data access happens from the client, with the exception of deletes. When a client does a delete, he essentially puts the file in the trash, and it's the MDS's job to come along and clear that up later. And what that lets us do is have really, really fast deletion from the clients, so that they don't have to iterate over these potentially thousands or tens of thousands of striped objects, and we do that in the background. So if you delete a file and you notice your space isn't freed yet, give it a minute or two, and the MDS will get around to it. The client side, I mentioned we have kernel implementation and user space implementation. In general, it's a fairly simple piece of software. Almost all of the intelligence lives server-side, but it does from time to time matter. So depending on your workload, if you have a small number of very demanding clients rather than a large number of lightweight clients, you might find that the actual client performance becomes an issue, and you might start caring about whether you're using the Fuse client or the kernel client. The kernel client tends to be a little bit more efficient just by nature of the interface that Fuse provides us. It's less easy to do efficient caching and avoid extraneous metadata operations with Fuse than it is with the kernel. I see a question.
You mentioned the extended attribute interface to the file layout.
Yeah.
And that's a relatively recent change that it's only available via X attribute. So how does that impact the compatibility with the kernel client? And if it does, what other such types of impacts can we sort of expect in the future?
Right. So the kernel client remains compatible. That interface change was because the way we were setting layouts before was a little bit unsafe, and we wanted to put nicer error handling in. And so that went in the VXAttra interface, and we deprecated the old interface, not because it didn't work anymore, but because we didn't really want people using it. It was a little bit unsafe. The general question of how do we keep the kernel client up to date, it's a challenge, because the Linux kernel is released on a different cadence to Ceph. So obviously we try and get our stuff upstream as soon as we possibly can. In future, now that we're part of Red Hat, we're going to be looking at what type of backporting we do to stable kernels so that people can get new interfaces on a stable kernel. But in general, yes, there can be a lag there, and that's one of the reasons that the Fuse client exists, so that if for any reason you want to do something which isn't yet supported in the kernel client, at present there isn't anything like that, but there might be in future, you would have that option of getting that client functionality without having to update to a recent and possibly less stable kernel.
Is there a current functionality, for example, in the MDS that can say, that where the MDS can basically say to a client, hey, you're too old? Talk to you because
yes. Yes. So Ceph in general, not just the file system, provides a bitmap of feature bits. And when clients start talking to each other, they exchange that bitmap. And so the MDS, like the rest of Ceph, will refuse to talk to things which don't implement the right feature bits. For the file system, recently we've had some functionality that wasn't so much a feature as a more safe behavior, and so we're currently looking at adding an explicit protocol version to the client-server protocol and giving people a warning rather than refusing if they have an older client. So the thing that's prompted that at the moment is adding new fencing functionality for clients, and older clients might not respect our fences, so they will work fine, but a conservative admin might want to know that he's got some of these potentially dangerous clients out there. Okay. So paying attention to clients matters if they become a performance bottleneck. It can also be important on a system that's having behavioral issues, if it's failing to respond or seems to have jammed up. Quite often people will say, my file system has frozen, and the server side is actually fine. What's happened is a client has misbehaved and is failing to relinquish some locks on some metadata. So it's important, if you are operating CephFS, to go look at clients. If your system seems not to be responsive, they can often be the culprit. Can I have a time check?
23 past 11.
Oh, good. Plenty of time. So the way that metadata ops get persisted and managed on the server side is a little bit interesting in CephFS. So, like many file systems, we have a journal. In our case, the journal is written to RAIDOS rather than directly to a block device. And it's important to be aware of that journaling to understand the latency behavior of the system. So when you commit a metadata operation, like creating a file, you have the sum of your network latency to the MDS plus the latency of the MDS to RAIDOS. One of the ways that you can take advantage of that knowledge is to put your metadata onto a different pool than your data. So when you create a Ceph file system, you tell it, I've got a data pool, I've got a metadata pool, and it might be the case that you want to use higher-end, more expensive storage for your metadata pool so that your latency on journal writes is lower. You might also want to consider the locality of your metadata pool with respect to your MDSs, potentially even putting OSDs for the metadata pool in the same machines, or at least the same switches, as the MDS itself, if you care about metadata latency. There are lots of workloads like the aforementioned sort of big disk images on an NFS share type workloads where metadata latency matters much less, and you might not need to worry about that at all. It's also important to be aware that as long as metadata has been written to the journal but not yet flushed to the on-disk data structures, it's pinned in cache on the MDS. And so we are deep in implementation details here, but it matters because your memory usage on the MDS is something that you have to keep an eye on. If you have a very long journal, then you can very rapidly build up a very big in-memory cache of the metadata, which you can't flush because the journal hasn't been flushed yet. So when you think about the length of journal that you permit in your file system, you have to think about that memory ceiling as well. And there's a sort of general piece of guidance that MDS servers should have lots of RAM in. The Ceph architecture expects that you will have a system with enough RAM to store most of your hot metadata, which isn't generally a problem. With the price of RAM these days, it's not an issue. So the workload-dependent nature of this stuff manifests itself in other ways. So some people will have a workload where they write a lot of metadata and then want to read it back. Some people will have a workload where they write a lot of metadata and hardly ever come back and access it, for example, if it's a backup. So that might influence how you configure your system as well. If you have more of a streaming type workload, then you might want to ask for a comparatively small metadata cache, because you know that you're not going to need to come back and hit that stuff in memory anyway. There's some level of configurability here. If you set MDS cache size, then the MDS will start trying to free up RAM when it reaches a certain number of inodes in cache, assuming that that doesn't conflict with the number that are currently pinned because of being in the journal. The other caveat for that setting, if you try using it and you find it doesn't work, is that the clients all have to play ball for this to happen. The other reason that an inode can be pinned in cache is because it has been granted, a lock on it has been granted to a client, and we can't take it out of cache until the client has relinquished that lock. So if you had a slow or misbehaving client and you found that your cache size limit wasn't being respected, that would be an example of a situation where the admin or the support person would have to look at both ends of the connection to work out what was going on. And keeping that cache warm is important in a failover situation. If you've got tens of gigabytes of data in cache, you don't want to have to reload all of that from various places on disk when you fail over from one MDS to another. For that reason, we have a mode called standby replay, where a standby MDS will follow along with the journal of an active MDS and populate its own cache based on that journal. So it's just passively following along the journal until the point where it has to take over, and at that point it already has a hot cache and it can fail over very quickly indeed. This is, again, an implementation detail, but one that's important to understand if you're interested in performance and performance limits. So in general, the job of the metadata in a file system is to map from a path to an inode. I've got foo/bar, and I want to know that it's inode 123. Great, that's what we're optimized for. In certain cases, you need to go the other direction, which is really annoying. Because you have to keep this whole backwards index around just in case. You have to do one of these things. And the two cases that use it are hard links and NFS handles. So the NFS client protocol allows for clients to forget the path of a file they have open and only remember the inode number of it. So in order to implement an NFS server efficiently, you have to be able to do this reverse mapping when a client says, yeah, I've got this file open, I don't remember what it's called, but close it for me. And you have to go and resolve the path. And hard links, clearly, it's because if a file has multiple names, one of the names is just going to refer to the file by the inode number. And in order to open the file via its alternative names, you have to be able to resolve back the inode number. So I'll finish the slide and then I'll come to you, okay? So it's expensive to store that index. It would be nice if we didn't have to, but we can't change POSIX. We have to let people have hard links. And the way we mitigate the expense of doing it is by taking advantage of a by inode mechanism that we already have. So you remember I mentioned that data objects are stored by inode number and offset. So what we do is we take the first data object in a file, which will be the inode number with a 0 offset, and we put what we call a backtrace, which is basically the path, on that object. Which means that we can go resolve by inode if we have to without having any extra objects. The reason I mention this detail is because it does show up in the behavior of the system. We are storing metadata effectively in our data pool now. So that nice behavior of being able to allocate a fast metadata pool has been compromised a bit here, because some of our updates are now, from the MDS, are now going into the data pool when it has to update these backtraces. And of course there are just extra IOs. If, for example, you have an empty file that ordinarily wouldn't have had any data objects, you now have to create one for the backtrace in any case. There's one really nice advantage to it as well, which is that now the data pool in itself contains all the paths for the files, which means in a disaster recovery scenario, if you've completely hosed your metadata pool, you can still, to some extent, recover your file system based on the data pool. And that's just a nice bonus. We haven't written a tool to do that yet, but it wouldn't be very hard to write at all. There are some ideas for improving the latency situation with backtraces. So, for example, getting the client to write the backtrace when it writes the data to the file. But that's a little bit complicated to implement because we can't count on it always doing it. And in general, we can't trust clients, so we have to keep it simple for the moment. And so if you look at the number of RAIDOS ops being done from an MDS and you wonder why it's twice as high as you think it should be, it's because of writing backtraces. So I mentioned we have snapshots and recursive statistics, a little bit more detail about those. So snapshots take advantage of an inbuilt ability that RAIDOS has to do snapshotting on data objects. So that's the same thing that's used in various RBD scenarios to have efficient snapshotting without having to do a bunch of copying. There is also a bunch of clever code required in the MDS to handle the metadata side of snapshotting, and that is currently known to be unstable. So when people are evaluating CephFS, we recommend that they don't enable snapshots, and in fact we have a flag in the software that disables snapshots, which is enabled by default. The underlying idea of using RAIDOS for snapshots and having subtree snapshots is sound. The implementation of this might change a little bit when we bring it to the point of being production ready, because at the moment it's arguably too general. You can snapshot any directory at any time, you can create snapshots within snapshots, and so on. And so we might look to creating a slightly more conservative implementation of snapshots that would meet the real life use cases, rather than having something that's currently a little bit over-featured and quite hard to get right in the implementation. And recursive statistics, the important things to know are they are lazily updated. That's true of statistics in many file systems, but be aware of that. So there can be a few seconds lag in getting those updated. And the key thing about these is they avoid spurious metadata operations, which otherwise can be quite expensive, traversing a tree. But also, these can be useful if you're building a backup solution. If you want to back up files modified since a certain time, you don't have to go all the way down your file system looking at modification dates or changes in size and so on. So there could be an interesting opportunity to build something that integrates with backup tools that takes advantage of recursive statistics. And just a little bit of practical to go with the theory, this is what it looks like if you actually want to set up a Ceph file system today. So the Ceph deploy tool supports creation of MDSs. That's a single line command. This is assuming you already have a RAIDOS cluster that's set up. You need to create a pool for your data, a pool for your metadata, and then ask Ceph to create a new file system. And that's not a data operation, that is just an administrative operation, so that Ceph knows, or specifically the Mon cluster knows, that there is now a file system. The MDS should be allowed to start up. That MyFS there, we added that recently, the ability to name file systems and list file systems. I'm using the plural. The current implementation only allows one file system at a time. But providing multiple file systems is not a conceptually hard thing to do. We just haven't got around to doing it yet. So at the moment, it's one file system namespace per Ceph cluster. But hopefully at some point someone will get annoyed about that enough to send us a patch that fixes it. And then once you've created that file system, your MDS will notice that it's there. It'll start serving metadata operations, and you'll be able to mount that from a client by just doing mount-t CephFS and putting in the IP address and the port and giving it a mount point. So at the point where you have multiple file systems, when you would be doing the mount, you would be typing IP address /myfs. Or another file system name, and that would remain backwards compatible, so there would be a default file system from the days where you could only have one, and if you omitted the name, you would get that one, and if you added a name, you would get one of the new ones. So the work, if anyone is interested in doing it, the work required to do multiple file systems isn't that hard. It's mainly a change on the Mon to have it manage the presence of multiple file systems, and a change to the MDSs and the clients to just tag along a file system ID with the operations that they do. So I have this, we're not working on that right now, but I have this feeling it'll happen sooner or later because it's kind of a piece of low-hanging fruit. One new thing in the recent Giant release, sorry, the forthcoming Giant release, is that we can now see the host names of clients that are connected. So previously, when you were trying to manage your clients, you could just see their IP addresses. We added a mechanism for harvesting metadata from clients. Not terribly impressive when all we show you is the host name, but it could be pretty interesting to have other pieces of metadata from the client. For example, if your client is responsible for serving to a particular VM, you might want to put the VM's name in here so that when you're managing the clients from the server side, you can see what's what, and potentially also we might add some per client statistics, and if you added the right IDs to reflect your use case, VM names, HPC job IDs, that kind of thing, you might be able to get nice per job or per VM file system stats rather than having the blunter sort of per IP address stats. So summing up what you need to know in practice to set up CephFS today, lots of RAM in your server. Pay attention to your clients. If something seems to be stuck, it may not be the server, it may well be a client. CephFS is under very, very active development, and that includes a lot of bug fixes. So whereas with Ceph in general, you get the best stability by going to the last sort of enterprise-supported release, if you are evaluating the file system, pick the most recent development release, because you'll get the most recent file system bug fixes in that. And the conservative configuration that we're focusing our test efforts on at the moment is having one MDS. The MDS has a dedicated server. We're using the kernel client for the most part, and you don't get to enable snapshots. And there is another feature called inline data where we send small file data via the MDS, and you don't get to enable that either if you want the best chance of not hitting any of the bugs. So that's sort of why it's not quite considered production ready. So I stole this from one of Sage's presentations, that Ceph is awesome, RGW is awesome, RBD is awesome, Brados is awesome, CephFS is nearly awesome. So the focus of our development at the moment is getting from nearly awesome to awesome. And that mainly means resilience, giving people something that they can trust. So we have to not corrupt things. We're already pretty good at that. We have to stay up. We're not crash. We're mostly pretty good at that as well. There are some cases where we assert rather than doing proper error handling if something's going wrong with the underlying cluster, but for the most part, we stay up and running. Handling the corner cases is a big focus as well. So I've been working on handling what happens when you run out of disk space on a system, what happens when your MDS cache gets big and you start having to order clients to remove locks so that we can evict things from the cache, which is all very, very sort of detailed-oriented stuff, but it's the last 10% of the software project that inevitably takes half of the time. Making things more visible to users is important as well. The recurring complaint, my file system froze, is something that we need to give people the tools to translate into something more helpful, like, I've lost contact with this client. This client is up, but he's not revoking the locks that I told him to revoke. The MDS is up, but it's struggling for resources to do IOs. So identifying those situations and surfacing them at the moment in the Ceph status output that you'd get from the command line tool. And finally, providing the tools for when something has gone wrong or you suspect something's gone wrong to find and fix issues. So that includes adding a file system check tool, but once you've checked your file system and you found something wrong with it, providing the tools to fix it as well. And that's a way for us to hedge against software bugs, which inevitably will happen, and also against people running CephFS on less than reliable systems. So if someone wants to live a little bit dangerously, or even more dangerously, and run CephFS on a machine that only has two-way replication on the Rados cluster, and they happen to lose 2 disks, we'd like to be able to say to someone who's lost 5% of their data that they can still access the other 95% of their file system rather than hosing the whole thing. And the path to doing that is to provide these tools. So the file system check, the online diagnostics, there is some work specifically focused on the journal, because that can be, if you want to break a Ceph file system, the quickest way to do it is to go and pick 32 bytes of the journal and zero it out, and there you go, the whole thing's broken. So there's a focus on being able to inspect the journal, being able to repair the journal, and that's primarily a tool for people supporting the systems to use. It's not something that you can generally do auto-magically, because if you had auto-magically realized the problem, you wouldn't have made the mistake to begin with that had led to it. So the manual tools are important there. Other sort of feature-ish stuff. Previously we had flock support in the kernel client, but not Fuse. Now we have it in Fuse. And we have some patches which are waiting to land at the moment from a third party for providing quota support for CephFS, which is something a lot of people have asked for. So it's about recovering from damage. The first step of that is identifying the damage. So we lose data objects, we lose metadata objects, and that might mean that we get into a situation where recursive stats might become inconsistent. What's in the journal might cease to match what's on disk. And as I was saying, the repair is automatic where we can, but the manual tools are important as well. The client management stuff is improving at the moment. In addition to providing the ability to list and evict clients, a more robust fencing mechanism is going in. So if you lose contact with a client, you cease to trust it, you can blacklist it at the Rados level and then safely allow other clients to take over without worrying that a rogue client might be sending writes in the background. The online diagnostics that have been added recently, a lot of these have come out of our own dog fooding of CephFS. So we're using it on our test cluster to actually store the results of the tests. So the results of the CephFS testing get stored on CephFS, which is an interesting catch-22 if it's broken. But so we were seeing bugs where a client would refuse to respond to cache pressure, refuse to release locks, and in general making a more transparent means of dealing with these sort of situations so that people don't have the frustration of just having a stuck file system. So there's a new tool called CephFS Journal Tool, which will give you a user-readable, well, a human-readable, assuming that human is a software developer, expression of your journal, and will allow you to snip out bits that don't work. So if you had an issue in your journal that referred to a particular client session, you would be able to say, right, I want to go into Rados and nibble away all the messages in the journal which refer to that particular client session, bring my MDSs back up, and it's as if nothing ever went wrong, other than that client would now be evicted. And we've also updated the on-disk formats used for this in the interests of resilience, so adding some magic words here and there so that when we want to recover something that's damaged, we can do so. The resource limit handling, the inode space, the cache size limits, the workflow here is very much write a test, see what breaks, go fix it. So there's this sort of blend of test and development that we're doing at the moment to make progress here. And one area that will probably come up quite soon as well is the issue of what happens when the MDS becomes I/O bound. If it's saturating the Rados cluster or someone else is saturating the Rados cluster, we have this race between the writes that we're doing for our journal operations and the writes that we're doing to evict things from the cache. And we will quite possibly need to add in some new flow control stuff so that rather than the MDS blithely continuing to accept metadata operations and they're just queuing up at the Rados level, having some flow controls so that from the client's point of view, it would start to see its metadata operations not be accepted until the MDS had caught up and was able to flush to Rados. So the ultimate answer to is CephFS production ready, other than being, it depends on your use case, is does it pass the tests? And do we have enough tests? So for Ceph, we have a test framework called Teuthology, which is very powerful and fairly comprehensive at the Rados level. And it provides a lot of long-running and what we call thrashing tests. So running the system for hours at a time with fairly active workloads and just killing OSDs, killing MDSs all the time. So there's still some way to go to extend that to cover the file system well, because we need to be thrashing clients, which we're not doing at the moment, and we need to be thrashing sort of error conditions like periodically filling up the system and just checking that the system progresses in those situations as well. There are third-party file system tests, which fortunately exist because people have written file systems before and they've written tests for them, and we can use those as well. And those are very useful to us as well. And one thing that's quite new is a small framework for writing functional tests in Python for the file system. So rather than this sort of run a workload on it, check nothing crashes type of testing, the ability to, when you've come and submitted a patch and implemented a new feature or behavior, to say, right, hold this part of the system in this state, poke this, check that, in a much more mechanical way, rather than just the robustness testing. And your testing, you the community, is extremely valuable to us because you will do things that we have not thought of doing. So if anyone wants to try out CephFS, we encourage that, not on your production systems, but we encourage it. And if you can give us test cases and specific bugs from that, that's fantastic. So coming up in the future, you tell us what you need. Recently we did a survey on the mailing list that highlighted some stuff we already knew, so the need for a robust FSCK, the hardening of multi-MDS systems as opposed to just a single MDS system is really important because a lot of the promise of CephFS is in the multi-MDS case. We need to make that work well. And quota support appears to be important to people as well. But, come to the mailing list, come on IRC, come and talk to me afterwards, tell me about what you'd like to use CephFS for and what features are important to you. And the use cases can be quite divergent as well. Some people are talking about you doing backups, some people want to build an NFS gateway, some people want to run Hadoop workloads. And again, come tell us what you want. And report bugs. Don't just send a message to the mailing list saying your file system doesn't work. Report the bug. Ross already mentioned the Ceph Developer Summit. That's coming up soon. The file system will be a big topic there. And that's all. Thank you very much.